Well, hello. For those of you listening, I'm David. It's semester 1 2016 and I'm doing a revision seminar for Engineering Mathematics IIA about Fourier series. And really I'm just going to share with you what I think I've figured out so far, basically. So, the philosophy of Fourier series is to rewrite functions as combinations of causes and sines. So that's what I'm aiming for. So my goal is rewrite function as a of causes and sines. That's the idea behind it, and that is an appropriate apostrophization there. Normally plurals don't have apostrophes, but cos and sine are abbreviations, so it's okay. Making sure, as coordinator of the writing centre, I need to know these things. Not that I work there. So in a similar way that a Taylor series is a rewrite your function as an infinite polynomial, we're going to rewrite our function as a combination of causes and sines. And to be more accurate, it's going to be sort of something constant and cos x and cos 2x and forever, and also sin x, sin 2x and forever. That's the idea behind it. Okay. However, there's a few caveats. It's only going to work if your function's periodic, because cos and sine are periodic, and so it's only going to work if your function's periodic. So, no. Only works if the function is periodic. And it won't be cos of x and cos of 2x and cos of 3x if your function doesn't have the right period. So it has to have a period of 2 pi in order for it to use that version, otherwise there's a different version. So period 2 pi, that one there. And if you want a different period, you have to adjust it, and I'll write that down in a second. But that's just the philosophy of what we're going for there. Okay, that's just my intro. Right. Just writing introduction. That's just my intro. This is what we're trying to achieve there, and I'm just going to have a quick example that's not the traditional version, just so you can see what I'm getting, what I'm thinking about this. So just as an example, f of x is like cos x squared, for example. That function, it should be possible, because it has a period 2 pi, to rewrite it as a combination of causes and sines like this. So, but when I say period 2 pi, it doesn't necessarily mean that it takes a full 2 pi to come back to where it started. It just means that it does come back to where it starts within 2 pi. So, alright, so I can, without knowing anything about integrals or any of that stuff, I can figure out with some things what their Fourier series is, by just rewriting them as combinations of causes and sines. Like, I know that cos of 2x can be written as 1 minus 2 cos x squared plus, sorry, no, damn, I always get that wrong, just a second. it's cos squared minus sine squared, like that. And I know that if I want this to be about cos squared, then I could replace the sine squared with 1 minus cos squared, and I'll get 2 lots of cos minus 1. And so if I rearrange this, I'll get, I can put the 1 over there and divide everything by 2, and I'll get this. Like that. Now this isn't a thing, I'm not wanting you to remember this procedure, I'm just making a point. So my f of x, which was cos x squared, is a half plus a half of cos 2x. And now it's already been written as a combination of coses and sines, well, just coses. And so in this sense, it's like if I had a0 and a1 cos x and a2 cos 2x and so on, I have a half and a half cos 2x. And everything else is 0. Okay, that's what I'm thinking about there. So I'm just pointing out that if you can write it as a combination of coses and sines and a constant at all, then that's already the Fourier series. So basically that's saying that actually A0 is a half, A1 is 0, A2 is a half, and AM is 0 for m greater than or equal to 3. And all the BMs are 0. That's what that's saying. So just what I'm pointing out, and this comes up when you do your second order partial differential equations, because often in your exam it'll give you something that's already a combination of cos and sine. So you don't have to figure out the Fourier coefficients because it's already been done for you. Okay. And it also points out it doesn't have to go on forever. Sometimes it stops. Okay, however, there is a way of calculating it, and one of the things I wanted to do was to recalculate this one using the integrals just to check if I've got the right answer. So now I'm just going to write actual formulas. So that particular method there will work if you know it's got period 2 pi, but sometimes you have to adjust the period. And so this is the, the Fourier coefficients. So A0 is that, AM is that, and BM and this works for f of x periodic, and it goes from minus L to L, basically, and then it repeats itself outside that domain. I like, instead of saying it has period 2L, I find it much easier to actually think about it, which it does have. It takes 2 L's to get from minus L to plus L. I think about it as going from minus L to L, and then it matches my thing. So basically that's how you do it, and then when you sub that into the other one, these numbers when you calculate them are the coefficients. It may be easier to remember if you think about it as sort of cos mx, and then it's sort of times pi divided by L, if you prefer, rather than seeing it as m pi x, seeing it as pi on L times mx. Because if the period, why is that? Have I done that wrong? Surely there's a 2 there somewhere. No, it's okay. It's all fine. Because the period used to be 2 pi, and so to change the period we had to times by pi, which makes the period 1, and then divide by L, which makes the period like. which makes the period from, we're dividing by pi, it used to be from minus pi to pi, and then we divide times by pi and it went from minus 1 to 1, and then we divided by L and it went from minus L to L. It's okay, good. Sweet. Just making sure that I've got that right. So you, yeah, but this is the standard one, and if it goes from minus pi to pi, then the pi and the L cancel each other out. Okay, sweet. Just making sure I've got that right. Okay, and that's basically the deal. So what I wanted to do was to just redo a couple of them and see what happens. Well, do one of them. I should point out that if your function is already, if f is odd, then that will mean that all the a's are equal to 0. And if f is even, that will mean that all the b's are equal to 0. So even functions are only made of cos, and odd functions are only made of sine. And that's because cos is an even function and sine is an odd function. So if you can look at your function and know straight up whether it's even or odd, you can just ignore half of the Fourier series. You only need half of it. Okay, so I just want to do an example. And I want to do that same example just to make sure that everything's working the way it ought to. Okay. This may be a bad idea, but I'm going to give it a go. So A naught is, yeah, it is a bad idea, but anyway. Okay. Like that. And I would have to integrate that, which means I would need to use my trig identity, my trig formula to do it. So it's going to, yeah, it's all redundant, but anyway, I'm going to do it anyway. But my L is actually, so this one's from minus pi to pi, so my L is actually pi, right? And normally to integrate cos squared, you'd rewrite it as a trig identity. And then you do it. So what happened there is that half got an x attached to it. The half from the half cos 2x is still a half. The cos 2x went up to sine, but because of the chain rule, I had to divide by the 2. This is the chain rule in reverse. And so I get sub in pi and sub in minus pi and then the sine of 2 pi and sine of minus 2 pi are both 0, and half of pi minus a half of pi would be just pi, and so I get half, as I should, because the answer was a half before for A0. And if I wanted AM, so it would be M pi x on L, but L is pi. So I've got multiple ways of attempting to integrate that. And most of these things work with integration by parts, right? So, yeah. Now we can give it a go. I suppose if we I mean, differentiating the cos would probably be the easiest. So we can give that a try. Integration by parts, hey?
Is it 1 on pi?
Oh, it is. The 2 pi is only for the 0, isn't it? You're right. So what I've done is I've done integration by parts, but I've whacked a 1 on pi in front of everything and a minus pi to pi. So if I differentiated the u, what do we get? So the u is cos squared and it's still a cos squared. And the v, I have to integrate that cos, which will become a sine. And then, well, there's not enough spaces there. The u dash should be 2 cos x, and because of the chain rule, a sine x as well. And then the v is still 1 on m. Okay. Damn, that's worse. Alright, well, worth a try. Well, if m times pi, sine of any integer multiplied by pi is 0 anyway, and m times minus pi, sine of any integer multiplied by pi is 0 anyway, so this bit's all 0. And then this other bit, I've got a minus in both of those, and a 2, and I'll bring the m, so I've got 2 on m. And that's not really any better, is it? Alright. It was worth a try. And so then if I did the integration by parts again, I'd have to integrate the... Oh no, that's not too bad. Look, I can use ordinary substitution to integrate that. Because look, this is the derivative of that. Yes! Ordinary substitution. So... let me just go... So let u be equal to sine x, and du on dx is cos x, and so my cos x sine x squared dx. Sorry, just a second. So my du is cos x dx, which means that that bit there is my du. That's u squared. If x is equal to minus pi, then u is equal to sine of minus pi. Yeah. And if x is equal to pi, then u will be sine of pi, which is also 0, isn't it? This is not looking good, is it? Because they're going to all be 0. From 0 to 0 of u squared du, which would be, of course, 0. Okay, well, most of them are 0, but I reckon that means that I probably should have paid more attention, because if m... Oh, that's an m pi, isn't it? It's not just a sine x, it's an mx. Alright, these are some good pitfalls to keep track of. But that is a sine x and a sine mx, isn't it? Ah. Right, it's not a sine squared. Damn. I'm going to chuck that page away. Alright, so there's a pitfall for you. Because we're going to get cos x, sine mx. And that is not going to do anything good, is it? You know, now, unless the m is 1, right? Because then it will turn into the thing we just had. But I actually, cos x sin x is made of sine as well. So, actually this is going to make a good point. Cos x sin x. Well, sin 2x is half of cos x sin x because of a trig identity. Oh, sorry, sin 2x is 2 of sin x cos x. So I'm going to get this because sin 2x is 2 sin x cos x. I can replace that like this. And there's this rule about what happens when you integrate combinations of sine. If they're both sine of something, and the two things next to the x's are different from each other, the answer will be 0. And that's because all of the sine mx's are orthogonal to each other. And when in the sense of functions being orthogonal, which means that they integrate to give 0 when you do that. So that's one of the rules that we need to keep track of sometimes. That if you do see a sine and another sine next to each other, if they're different, if the coefficients of x are different, then the answer will be 0. And so, if m isn't 2, we're going to get that am is minus pi to pi of a half of sine 2x sine mx dx, which is going to be 0 because it's the integral of two different sines multiplied together. And if m actually is 2, we'll get sine 2x and another sine 2x, and I'd have to integrate that, which I could do with the trig identity. I believe it's what did I just write before? It was like cos of 2x is cos x squared minus sin x squared, which is 1 minus 2 sin x. So sin x squared would be a half minus a half of cos 2x. And I've got sin 2x, so it's going to be a half minus a half of cos 4x. Wow, okay. This was way more complicated than I thought it would be. Okay, and so we get I suppose that this half can come out the front, and we've got a half of x minus a half times a quarter of sine 4x and minus pi to pi. But when I sub in pi minus pi into this bit, it'll be 0 both times. So it's just going to be that bit. And so I'm going to get, and my m is 2, isn't it? My m is 2. And so, let's do some cancelling. That cancels with that. 2 pi. And we'll get a half of pi minus a half of minus pi, which distresses me because I'm not getting the answer I should, so I must have done something wrong. No, that's right, because I've got a half of pi and then plus another half of pi, which is pi. Good. Which is a half as it should be. Okay, so I've ended up with a0 is a half a2 is a half, and am equals 0 for the m not equal to 0 and 2, basically. Which is exactly what I should have gotten. And I know that bm is 0 for all m since cos x squared is even. Okay, so what's the moral of that tale? I don't know. Possibly that don't forget your integral methods from first year. A very important thing, which is what all this stuff hinges upon, is this thing here, that when you have a combination of multiplication of two sine of something x's, if they have different coefficients, then the answer will come out to 0 when you integrate it.
Is it same for cos?
Same for cos. If you have two of this, if you have a cos and a cos, they'll come out to 0. If it's different ones, if it's sine and a sine, it'll come out to 0 because they're different ones. If it's a sine and a cos, well, sine times cos is an odd function, so when you integrate it from minus something to something, it'll come out to 0 no matter what. So, yeah. But that's the whole, I mean, there was a whole bit of the lecture notes about the orthogonality of those things, and so they're orthogonal in the function sense, which means they integrate, the product of them integrates to make 0. So, useful thing to point out there.
What about divide?
Well, dividing would cause all sorts of pain,
Okay.
because you would have places where it's not defined. So that would be a weird-ass thing. I have no idea what the dividing would do. Yeah, I don't even know what that would turn into some strange things. I mean, you really divide them, you'll get some sort of combination of tan or something. Yeah, all right. Worthy question to ask. I've taught you well to ask the what-if questions. Well done with that. I threw one of these pages away, didn't I? That one there. Just making sure my pages are in the right order. Okay, so that's all well and good. And it works really well for functions that are already periodic. The thing is that most functions that are already periodic are already written in terms of cos and sine. And so it would have been, see, that took a lot of effort to do what I just did. But it wasn't necessary because I can rewrite that one in terms of cos and sine by just using trig identities to start with. And I had to use that trig identity in order to integrate it in the first place anyway, so it was quicker to just go straight to it. But what I wanted to point out was that doing the integrals actually gave me the right answer. Okay, right. So, the next question is, well, let's take a function that isn't periodic, we'll have to extend it to make it periodic, and do this again. Let me just think about it. That'll do. So that function, yeah. So that function is not periodic. It doesn't repeat itself. But what we're going to do is we're going to define it just on a small region. We'll define it like this for x between, say, -3 and 3. And then f of x plus 6 is f of x. So what we've done is we've done it from -3 to 3, and then we've made it periodic by repeating it every 6, because this is a width of 6. Technically, if you look at some things online, they won't even mention this. They'll just say this is only defined from -3 to 3, which is okay, because my sine and my coses will also be looking at that particular domain. But in essence, when you do these Fourier series, you're actually redefining the function to be periodic the rest of the time. So it's x plus 1 from -3 to 3. That. And that's the bit from -3 to 3. And then sort of outside this domain, we're going to copy it. but it's not in a sense, I don't really care what it does outside of there. Because a lot of the differential equations we use Fourier series to solve are about vibrating strings or, you know, chains with certain lengths, and so they're only defined on a certain domain anyway, so what it does outside of that is irrelevant to you, and if you need to make it periodic outside of that domain, go for it. But the rest of it is like this, right? It repeats itself. Like that. Okay. So this function is neither even nor odd. And so it's going to need both causes and sines in its Fourier series. If it was just f of x equals x, that's an odd function, it would only end up with sines. If it was f of x equals x squared, that would have been even and it would only have causes. So let's see how we go. So my A0 is the integral. Now let's see, it's 1 over 2L, so 6 in that case. From minus 3 to 3 of my function dx. Okay, so x goes up to half of x squared, 1 goes up to x, from minus 3 to 3. And so I'm getting a half of 3 squared plus 3 minus a half of minus 3 squared minus 3. So we've got a 9 on 2 plus 3 minus 9 on 2 minus 3, which is 6. So my A0 is 1. That's cool. But it kind of makes sense because I already had a plus 1. So that's telling me that the constant term is 1. So that makes sense. If your function has a constant term already, it will be equal to this constant term. That's nice. Okay, AM. So for m greater than or equal to 1, AM is 1 over L, which is 3, the function times cos of mx. Okay, so I'm going to have to integrate that. I could split it into two pieces. Sorry, the x cos mx and the 1 cos mx if I wanted. In the end, that's just going to be more work. It is two things multiplied together, so I'm going to have to use integration by parts.
Why isn't cos n pi x on L?
Oh yes, it is. Sorry, it's not just mx, is it? Because it would only be mx if the period was pi, but the period is actually like that, isn't it? Well done. Catching all sorts of weird stuff that I'm doing. So I'm going to have to do integration by parts. And actually, just to make it easier, I'm going to have to divide by that 3 later. I'm just going to go 3am is equal to this. And then I don't have to worry about putting the third everywhere, and I'll divide by the 3 at the end. So u v dx. Okay, so that's integration by parts. And one of them will have to have a dash and the other one won't. The x plus 1, if I differentiate it, will disappear. It'll become a constant. So I'll put the dash on the u and integrate the cos. Alright. So the u is x plus 1. And the v is the integral of that. So the integral of cos is sine. And I'll have to divide by that constant because I'm integrating. So that would be 3 on m pi. And that'll be from minus 3 to 3. And then this bit is the u dashed, which is 1, and the v is the integral that I've just calculated, which is sine 3x 3 on n pi dx. Okay, so let's investigate this a little further. If I sub in 3 into this, I'll get an integer multiple of pi. It'll be sine m pi 3 on 3 times 3, so it'll be sine m pi. So if when I sub in a 3 into here, it'll come out to sine of an integer multiple of pi, which is 0. Subbing in a minus 3 will also be an integer multiple of pi, and so it'll be 0. So this bit here is 0. I'll just put a sense. Sine plus or minus m pi is 0. That's the reason that that's 0. And over this side, sine is an odd function. This is just an integral of sine. And sine, this is sine times a constant. It's an odd function, and an odd function from minus to the matching plus is always 0 when you integrate it, because sine goes below the axis down to minus 3 and above the axis to plus 3, so the negative bit and the positive bit cancel each other out, and so we're going to get minus 0, and then sine of m pi on 3x is odd, and so the answer is 0. So actually my am is 0 for m greater than or equal to 1. That's kind of cool. And again, that does actually make sense, because my original function has an odd bit and an even bit. It's got an even bit here, which is the 1, and an odd bit here, which is the x. And so the only even bit is the constant, and so that's the bit that's going to get attached to the causes. See, by doing the problems, I'm understanding it better. I don't know how you feel, but I'm feeling better. So, to finish it off, my Bm will be 1 on L, from minus L to L, of the function times sine of mx, only it won't be mx, it'll be, I'll have to adjust it because the period is 3. Not, the period isn't 3, but because it's from minus 3 to 3 instead of from minus pi to pi, I have to adjust it. Okay, I'll do the same trick I did before. And I'll do integration by parts again. So let's see. U v dx. And again, if I differentiate the x, which was down here, that's where its derivative is, then it will go away, and I'll be able to finish it off. So let's see. The u is x plus 1, which is still here. This v is the integral of v dash, so the integral of sine is minus cos. And because of the chain rule in reverse, I'll have to divide by this. Okay. And the u dashed is, u was x plus 1, so u dashed is 1. And the v is the same v that we just wrote down, so minus cos of m pi on 3x. 3 on m pi. So let's see if we can do anything good. Cos is not nearly as friendly as sine. Cos, I do have cos of an integer multiple of pi, but coses of the integer multiple of pi's tend to be plus or minus 1 depending on whether it's an odd or an even multiple. So No, nothing I can do. I'm just going to have to deal with that. Let me just sub it in. So we've got minus 3 plus 1 cos of m pi on 3 times 3. 3 on 3 pi minus 3 plus 1 cos of m pi on 3 times minus 3 times 3 on minus 3 pi.
Is that 3 minuses?
No, that is 2 rubbed out minuses. Yeah. I just didn't have enough room for everything. I think I need one more bracket actually. Alright, okay. And then my integral, I will do that in just a moment. But I will at least make everything look prettier. Those 2 minuses can come together to make a plus. Okay. I do not like it, so I am. Oh, but cos of minus something is the same as cos of plus something, isn't it? Sweet. It's good. So what have we got? Minus 4 times, they cancel, 4 on pi cos of m pi minus, this is minus 2, and 3 divided by minus 3, there'll be a minus pi on the bottom, and I'll get cos of minus m pi. Just making sure I do everything one step at a time or I'm going to lose my minus signs. And then the other bit, so the other bit will be the 3 on m pi will still be there. Cos becomes a sine, and I have to divide by that thing there, so it's another 3 on m pi. Doing well. Let's see what happens on the next line. Okay, so I didn't change this bit, and then the minuses that are here cancelled, and then the cos of minus m pi is the same as cos of m pi because cos is even. And this bit down here, sine of, oh that's not a pi, sorry, it's a 3. So when I sub in x equals 3, I'll get an integer multiple pi. When I sub in x equals minus 3, I'll have an integer multiple pi again, so that'll be 0. And then I'll get minus 6 on pi cos of m pi. And the nice thing about cos of m pi is it's minus 1 to the m. Because if m is even, cos of 0 is 1, and cos of 2 pi is 1, and cos of 6 pi is 1, because they're all the same answer. Cos of pi is minus 1, cos of 3 pi is back to pi again, which is minus 1. And so you'll get minus 1 to the m. Like that. Brilliant. And so what have we got? We've figured out that was bm, right? Oh, that was 3bm, and so bm is actually minus 2 on pi. Because that was originally 3bm. There. Okay, so what have we got there? We've got that. So we have that my f of x, which was x plus 1, well, within that domain anyway, the A0 was 1, and then all the other causes were 0. I'm just going to put them in explicitly, right? One to infinity, sorry. 0 cos, like that. And then my sines were minus 2 on pi, minus 1 to the m sine. So that's my Fourier series, which, just to make it look prettier, is that. Technically it's only for x is between minus 3 and 3, well, and periodically, I suppose. Alright, so learned a few things. There's a lot of that whole sort of, oh look, the sign, when I sub it in I get an integer multiple of pi, and so it disappears. And there's a little bit of a, what is cos of an integer multiple of pi? It's minus 1 to the m. And I dare say that a lot of the time your on L will cancel with your L, and so things will turn into what they're supposed to be. And that just leaves doing one that is a half range, which I didn't talk about yet. So, doing okay. This thing here if your f is the right kind of function, then you don't need to go from minus L to L, you can go from 0 to L. Because if f is, say, an odd function, then this will just be 0. And if f is an even function, you can just go from 0 to L. And here, okay, well, just a second. If f's an odd function, we'll only be using this one anyway. And if f is an odd function, then an odd function times an odd function is always an even function. And so therefore, this is an even function, and therefore it's the same from minus L to 0 as it is from 0 to L, so I can just do it from 0 to L and times by 2. And if f was an even function, which means I'd only be using the a's, then the integral of an even function from minus L to L is the same as from 0 to L times 2. And an even function times an even function is still even, and so therefore it will be from 0 to L as well. So either way, I could just go from the middle to the edge instead of from one edge to the other. So so we can do the half range, right? In a way, it's really the half of the domain. I don't know why they call it half range, but half range, if f is odd, then you'll be able to just do the BMs and everything. You'll have to times it by 2, but you can just go from 0 to L. And that will be marginally easier because you'll be subbing in a 0. And if f is even, you'll have that your A0 is twice the size as it was before, and your AM is twice the size it was before, but only half the domain. And if f is odd, you don't need to do the A's if it's odd. And if f is even, you don't need to do the B's. Because you know that it will automatically come out that an odd function is only made of sines and an even function is only made of causes anyway. So that's the half-range expansions. It's taken me some years, well, days, because I've been thinking about this for years, but it's taken me a while to actually realise why that works. And it's because we're considering the A's and the B's completely separately from each other. Okay. So if I do my half-range ones, then my odd and my periodic extensions are a little bit different. So I had here a function that was neither odd nor even. Where's my x? Here, x plus 1, and it crossed over from -3 to 3, and it wasn't odd or even already. But if I have a function that's only from 0 to something, I can extend it into an odd or even already. This one couldn't be extended to be odd or even because it wasn't, it already crossed over this line. But if it only went to there, then I'd have a hope. So I'm really interested to see what happens if I use the same function, but only from 0 to 3. That's my plan.
Great maths.
So, okay. So the other one, different. To 3, not -3 to 3. Okay, just pointing it out. I get to choose whether to do the odd one or the even one. I choose to do the even one because we've already done some integrals for the bn's. We've already done some things with the bn's, so I have a feeling it would be useful to do one with an an so that we can use whatever strategies come up with that. All right. So let's do the even extension. Okay, so technically I don't actually care what the even extension actually looks like, except that the lecturer keeps asking me to do it. But I don't really care what the even extension looks like because most of the functions that I'm interested in actually only even exist between 0 and 3. I'm just sort of imagining that if I wanted to make it out of causes, it would need to be an even function. So, and it would need to be periodic as well. And so, when you make an even extension, so this is what it looked like originally, which I might put it in blue so that you can see it better. That's the original function. And first I make it even, and then I make it periodic. So the first step, this is my key. My key will be blue is original. Then I make it even, that's step 2. And so I'll do this. It's even now. Like that. And then I make it periodic. Which I shall use green. Like that. There you go. That's my key of the order I did it in, just so you can see. So first I make it even, and then I copy that. Unfortunately, my graph is nice and symmetrical here. It'll always do that if it's even, but making it odd would have been a very interesting thing. I'm just going to draw the odd extension while I'm at it, even though I'm not going to use it, just so that you can see what it looks like. And I'll use the same key, make it the original, and then I'll make it even or odd. So the original function was like this. Like that. And then what I had to do is make it odd, which means I need to rotate this around the origin, and it's going to be like this. And then I have to copy that left and right. Sorry, it's not particularly well drawn over there. So as you can see, the odd function, not very nice. And actually, just to make it easier to read the odd function, I'm going to just draw in nice and dark the dotted lines that connect them up. They have to be dotted lines because the vertical line isn't actually part of the function. So you can look at that, and the odd one is much less pretty than the even one. So I choose to do the even one, because it's a prettier function. If you're in an exam, you'll just be told, and you won't be able to choose whichever one you think is best based on the fact that it's even or odd. But this one's prettier, because look, it all connects up, so I'll use that one.
If it's not continuous, do we have to have bounds when we do the integrals?
No, it all works fine. If it's not continuous, it'll still be okay. Because you can still integrate something that has a jump in it. It will still work. And because you're only using half of it anyway, it's continuous on the half that you're integrating. So, yeah. What will happen is that when you do your Fourier series, that if you stop at any, it goes forever, right? But if you stop at any point and don't go forever, the Fourier series' answer at 0 will be halfway between these 2 points here. And the Fourier series will be halfway between those 2 points, which is here. So even if your original function wasn't continuous, this bit, the blue bit here, you could still do it anyway. You just have to split your integral into two different pieces. And actually, if your function has already got two different pieces, you have to split your integral into two different pieces. And I don't know if I have time to do one of those, but I might. Okay, so I'm just going to do the even one. My Fourier cos series for my even extension. And I know it's going to be a cos series because cos goes with the even ones. So my A0 will be 1 over, it's normally 2L, but it's only half, but it's twice the size. So it's 2 over 2L, and from 0 to L of my f of x, which is x plus 1. And what's my L? 3, isn't it? And so I'll get a third of a half of x squared plus x from 0 to 3. And the nice thing about that is that when I sub in 0, I will get 0. So that comes out to 3 on 2 plus 1, which is 5 on 2. So that's my A0 this time. Note that it doesn't match my 1 anymore, interestingly. But that's okay. The reason it doesn't match my 1 anymore is because this 5 on 2 is getting at the centre of this. It's not telling me where the bottom is, it's telling me where the middle is. So that's why it's not 1 like it was last time. It will work out when I get the causes. Alright, and my AM will be, normally it's 1 on L, but it needs to be twice as big. And normally it's minus LTL, but I'm only doing half as much. And the twice as big and half as much cancel each other out. I'm getting good at drawing my pi on L there. And I already did this integral last time. So I'm just going to cheat. So, and what was my L? It was 3, wasn't it? Alright, I'm going to move this out of the way so that I can deal with it later. And I would, at this stage, use integration by parts. So I'm just going to do it. And it's going to become equal to afterwards. And again, if I need to see all of it, there we go. My cos, if this one is the u and it will get differentiated at the end, then it will become a 1 and disappear, so I can do it this way. So let's see, my u is at this, I need a u, and up here my u is x plus 1. I need a v, and up here my v dash is this, so I'm going to have to integrate it. But because of the chain rule, I'm going to have to divide by that constant. And then let's see, my u dashed, my u was x plus 1, so my u dashed is 1. And my v is what I just calculated. Okay, now let's have a look at this. When x is 0, sine is 0, and when x is 3, sine of an integer multiple of pi is 0, and so again we get a 0 for that bit because of the way that sine behaves for integer multiples of pi. And this integral, well, the 3m on n pi is still there. I need more space than that, don't I? The sign will go up to minus cos, and the 3 on n pi will come out because of the chain rule, and then there'll still be a 3 on n pi that was already there. So those two minuses are going to cancel each other. So let's see, cos of m pi on 3 times 3 times 3 on 3 pi times 3 on 3 pi minus cos of 0 times 3 on 3 pi times 3 on 3 pi. It's not 3, it's m pi. Sorry. And let's see. Well, cos of m pi is minus 1 to the m. and cos of 0 is 1. And so we get, and we've got a 9 on m pi squared on both of them. We've got a minus 1 to the m and a minus 1. There we go. So it looks like my f of x, my Fourier series expansion for the odd even extension, is the a0, which came out to 5 on 2, and this. Because this is my, oh crap. Sorry, gonna have to just, I can't be bothered rubbing that out, I'm just gonna cross it out. That's not AM, it's 3 on 2 AM. So, I'm actually gonna get that AM is actually, divide both sides by 3 is actually that. No, other way around, isn't it? Oh, for fuck's sake. Times by 2, 6. Right. Divide by 3, times by 2. Yeah. It seemed like such a good idea to move it out of the way. Right, yeah. If I was being very clever, I would notice that when m is even, I get a 0. And I could turn it all into something that only has even numbers in it. That might look prettier. But I don't know if that's necessary. But it's just something that might be worth pointing out. Note, m is even, we get minus 1 to the m minus 1 will just be 1 minus 1, which is 0. So we actually only have odd terms. So actually, only the odd m terms exist. So I could, if I wanted to, go let m be like 2n minus 1, because I want to start at 1. And so we'll have that f of x. And if it is odd, then the answer is minus 2. And also, we'll do that in a second. Also, if m is odd, then minus 1 to the m minus 1 is minus 1, which is minus 2. And so we'll actually get, let m be an odd number, and then what we're actually going to get is this. N equals 1 to infinity 6 on 2n minus 1 pi squared times minus 2 cos of 2n minus 1 pi on 3x. If you wanted. It's hardly better, really. But, you know, we could have done that if we wanted. So, probably don't have to do this. I only mention it because sometimes they give you an answer and they go, well, show that this is the answer. And you go, how the hell did I get that? And it's because they did this little trick. They noticed that it was 0 every time that the other one was even or odd. Well, how long have we been going for? I have no idea. Does anyone have any specific questions they wanted to ask?
What is complex Fourier series?
What is complex Fourier series? I may not answer that today because I still don't know. I have a feeling it's to do with the way that cos and sine come up in the complex numbers. So, but I don't know myself because I've never studied this in a course, and since it's not examinable, did your lecturer say that? Sorry? It's in past papers. What did this semester's lecturer say?
Venus fluidities are just half range.
Yeah, so today I'm not going to deal with it because, you know, at this late stage in the game, considering we only have, 3 2/3 hours of drop-ins into opening time before your exam, I think it's probably time for me to get there. And maybe another day I will try and deal with what they are. But never having done a course on it, I'm not going to commit myself to figuring it out today, if that's okay. I guess the only other thing to say is that be really careful. Actually, I will just put this last bit in because I want to, just do an example. I won't finish it off, but I just want to point it out. What if your function was already made of other functions? And your classic is when you have like x from for x between 0 and say 1, and or maybe I'll do it from some other number, from 0 to 2, and just give me a second. And minus 2/3 of x minus 3 when x is from 2 to 3, something like that. It's got two different formulas in two different places, and so when you do your integral it's going to be a bit of a problem. So I'm going to do the odd extension. So first let me draw it. Should really do them actually equally sized. So I know that x and minus 2/3 of x minus 3 are both straight lines, and so it's actually quite easier to draw them than other functions because they're both straight lines. This one's a straight line. It goes from and so I can just figure out what they are at the ends and connect them up. When x is 0, the answer is 0. When x is 2, the answer is 2, and I just connect them up. With this one here, when x is 2, the answer is, oh crap, have I done something wrong there? Totally have, sorry, it's 3 on 2. Yep, sorry, 3 on 2. No, it's still wrong. Sorry, I'm just going to have to fix the whole function. Give me a second. That would be right. Right, it's just minus 2. Sorry about that. So when x is 2, the answer is, so when x is 2, for that second half, the answer is minus 2, minus 3, which is just 2, so it goes through that point. And when x is 3, the answer is minus 2, 3 minus 3, which is 0, so it goes through that point, and being a straight line, I can just connect them up. That's the idea here. So for x between 2 and 3, I'll just figure out the answer. Let me just make that a little prettier. It'll be exactly the same thing, just prettier. So when x is equal to 2, y is minus 2, 2 minus 3, which is minus 2. And when x is equal to 3, y is minus 2, 3 minus 3, which is 0. And so I connect up the 2 points, 2, 2. Sorry, it's plus 2. 2, 2, and 3, 0, and connect them up because I know it's a straight line. And the odd extension would be making it odd first, like that, and then copying that. Like that. Except I should really be more careful about what it looks like. It's not quite so symmetrical, is it? Yeah. Anyway, you get the idea. I'm copying it. But it's this bit that I'm really interested in here. So, if I were to do my thing, I would say that I'm going to do my odd one, so my Bn, which would be the 1 over 2 times the period, this width, which is 3. It goes from 0 to 3. Goes from 0 eventually to 3. So 1 over 3, only it will be 2 over 3 because it's a half range expansion. And it will be from 0 to 3. And it will be my function sine of m. Okay. But my function has different formulas in different parts of this, so it's actually going to split into 2 different pieces. So I'm going to do this trick. And go, well, the bit from 0 to 2, the formula is x. And the bit from 2 to 3, the formula is minus 2x minus 3. And I'll have to do both of those integrals separately. Both of them by parts. Sadly. Yeah. So yes, I'm going to have to do both of those integrals separately. I'll have to do the 0 to 2, and if I was going to do my working, I would actually split them up. I would go the integral from 0 to 2 of x sine n pi on 3x dx equal blah blah blah, and I get an answer at the end. And then I would go the integral from 2 to 3 of minus 2x minus 3 sine n pi on 3x dx would be equal to blah blah blah, and then be an answer for that. And then I'd go, well, 3 halves of Bn, Bm is whatever they are, and then I'll divide by the, times by 2/3. That's not a 0, it's an oval. Yeah, there you go. That's what I would do. just pointing out that if you do, your function has different definitions in different places, you're going to have to split your integral into pieces. Excellent. I think that's everything I could possibly say about that this year, maybe next year, but you won't be doing it again next year because you'll pass with flying colours. I'll try again.